The logregC function is used to do logistic regression analysis, which is a special type of regression used to analyze binary outcomes. The logregC function has one required argument, formula, which is set equal to the regression equation to be estimated. We use a special syntax for formulas that you need to learn to use logregC. The logregC function supports a standard set of optional arguments. With logregC, you have options to specify observation weights, the dataset name, the number of digits you want to see after decimal points, and whether you want to print your results to an HTML file in your working directory. The function has additional, optional, and plot-related arguments. You can set the orci argument equal to true to obtain odds ratios with confidence intervals. You can set the fit.stats, ANOVA, and or PRE argument to true to obtain various measures of model fit. The plot-related argument, res.plots, can be used to generate plots of residuals. To be honest, logistic regression residuals aren't as useful as linear regression residuals, but we'll take a quick look at the res.plots argument anyway. To learn how to use the logregC function, let's work through some examples. Let's work on an example of logistic regression analysis using the logregC function from the RCPA3 package. So to run logistic regression analysis with the logregC function, we would obviously type the name of the function, logregC. It has one required argument, formula, and formula is set equal to a dependent variable as a function of one or more independent variables. And as I noted here in the comment line 7, the dependent variable must be binary, so it has two possible outcomes. An example from the NES data set, they have these really interesting examples about life experiences. I thought one was interesting was flying the flag, whether people fly the flag or not. So let's estimate the likelihood of flying the flag as a function of respondent's age, let's say, as well as how long they have lived in their community. What was the name of that? Lived address? Kind of forgetting the name of the variable. Address years? There it is. That was throwing me off. I was trying to type in years and it's YRS. The abbreviation threw me off there. So we will estimate likelihood of flying the flag. It's a function of age and address years. Let's get started with this. Okay, so in the output for logistic regression analysis, we get a table of the logistic regression coefficients. Looks kind of like the table of linear regression coefficients, but it's going to have a different sort of meaning and interpretation. Looks like there's a negative relationship that's statistically significant for both age and years. We get a table on the residuals and some additional model information. Now, if you think about it, if you look at this, you might assume that increase in age makes people more likely to fly the flag, and so the outcome of interest probably is no here, does not fly the flag. So age increases or decreases the probability of not flying the flag. It's kind of a handful to say. It's not really how we would have chosen to code it. And I also think it's a bit confusing because even with this binary dependent variable fly flag, it works in the logistic regression analysis. R is able to handle it, but you can't really tell from either the name of the variable or the output whether the outcome of interest is flying the flag or not flying the flag. So I think it's a good idea to get the dependent variable specified the correct way so the outcome of interest corresponds to the one value of the dependent variable rather than the 0 value. A good way to check how a variable is coded like this, I like looking at the variable's levels. So what's going to happen here is you've got the first outcome and then the second outcome, and then I believe the way it's going to code, if we don't specify otherwise, that the higher value will correspond to the outcome of interest in logistic regression. So this particular analysis is modeling the probability, the likelihood of not flying the flag, which is probably the opposite of what we want to do. So I would, to make the output easier, what I would do is create a dummy variable that is in line with really what you want to estimate, and to be more clear about it, both in the coding and in the analysis. So what I might do is use our transform C function to do a dummy variable transformation applied to the NES, the life experience fly flag, and then the response to make a 1 will be what I saw in the levels as the 1.yes category. And I'm going to assign this to a new object, a new variable in the NES data set called flies. Let's call it flies flag. Now that variable name was flag. So that variable name is a little better because it's, in the spirit of dummy variable, and indicating what the one category is. It's people that fly the flag. So I think I would start with creating this dummy variable, and then in our logistic regression, using our new dummy variable as the binary variable. And this, from the computer standpoint, doesn't make a big difference to R, but for us it's going to make this a lot easier to interpret now. We have the dependent variable is flies the flag, and we can see from the logistic regression coefficients the estimated effect of age is positive and statistically significant. So the older people are, the more likely they are to fly the flag. Similarly, the longer that people have lived at their address, each increase year at the address increases the likelihood of flying the flag, and that effect is statistically significant as well, as you can tell from the p-values. When it comes to logistic regression analysis, I don't think the logregC executing its required argument requires it's too challenging if you know how to use the regC function. So the syntax isn't all that difficult, but I really think the challenge of logistic regression analysis is getting the dependent variable specified correctly, because the computer is kind of happy to do it a misleading way, and you have to make an effort to have the dependent variable correspond to really what you want to investigate. And if you take the time, like I've done here on line 9, to create a binary variable that corresponds to what you want to investigate and use that binary variable in your analysis, it makes the interpreting the results of logistic regression so much easier. So the challenge is almost more, I think, in the setup for the logistic regression than estimating the logistic regression model using the logregC function itself. And if you set it up correctly, it works smoothly and is not particularly difficult to interpret. So we've done some basic logistic regression analysis, looking at the likelihood of flying the flag as a function of age and years at address. Let me show you some of the optional arguments you can use with the logregC function. One of them is fairly common, is to weight observations, and using the W argument, we would set that equal to the variable in the data set that weights observations. With this NES data sets, this is WT variable. And if we run that, it should output results for us, weighting observations to be a bit more nationally representative. Substantively, it's looking the same, positive effect of age and years at address on the likelihood of flying the flag. One of the challenges in logistic regression analysis is interpreting the results on a substantive level, because these estimates that we see in the table of logistic regression results, these are going to be in logged odds. And logged odds, the most common way to think about likelihoods, not as common as percentages or probabilities. Something that's more useful that can help us substantively interpret the results are odds ratios. And to look at the odds ratios, we can use this ORCI argument and set it equal to true. This will give us the odds ratios with their confidence intervals. It starts with a similar, tables, and then adds our odds ratios for logistic regression coefficients. Each independent variable gets an odds ratio, and it would read something like the odds of flying the flag increase by a ratio of 1.025 for each 1 unit increase in age. If you want to think about that change, the odds ratio, as a percentage change in odds, we see that in the fourth column here, percentage change in odds, and it would say something like the effect of 1 year of age is a 2.475 percentage increase in the odds of flying the flag. So that ORCI is helpful with the substantive interpretation of logistic regression analysis. Not as good as plots, but simpler to create just with the optional argument with the logregC function. Additionally, we have a few optional arguments that help us understand how well the independent variables explain variation in the dependent variable. We'll show you the argument fit.stats to generate some fit statistics for the logistic regression analysis. We also have ANOVA for analysis of variance report, PRE for the proportional reduction in error, and we're using these all the same way. By default, they're all false, and then to use them, we add the argument separated by commas and set the value of the optional argument equal to true. Okay, those are the ones. I think those are all the ones I want to show. So let's give these a run and look at the results. I've added 3 optional arguments, all kind of related to the explanatory power of the model. So let's start with our coefficients, table of deviance residuals, additional model information. And now we get the model fit statistics, a set of some different statistics that produce R-squared type measures for the model fit. Then we have a classification table and proportional reduction in error. The classification table is really the basis for this lambda measure of association, telling us how much our ability to predict flying the flag increases with knowledge of the independent variables. So our ability to predict whether respondents fly the flag increases by 0.085, or about 8.5%, with knowledge of the independent variables. And then we also have an ANOVA table that's, we'll highlight that the variables in our analysis are statistically significant and explain a lot of the variation that we observe in the dependent variable. And then with these model fit statistics, we have a set of measures, a chi-square measure of model fit assessed by the, you can assess whether the model is statistically significant based on the p-value. And we have McFadden's R-squared, the Cox and Snell index, and the Nagel-Kirky index. These are all different ways of producing an R-squared type measure for roughly the proportion of the deviation, that a proportion of the deviance of the model is explained by the independent variables. It doesn't have kind of the neat interpretation of R-squared. It relates to the improvement of log likelihood, the reduction of deviance of the model. But it's a pretty decent yardstick of how well these these independent variables do in explaining variation in flying the flag. So depending on which one we pick, say that we between maybe 4% and it maybe at the low end, 7.7% at the high end of the deviance of the variable is explained by the explanatory variables. A similar outcome to what we saw with the lambda measure 8.5. These are significant predictors, but leave a lot of the variation in the observed behavior of flying the flag to be explained. I don't want to get too deep into the substantive meaning of these measures, but if you want to have the logregC function produce them for you, these are the way to do it with the fit stats argument, the ANOVA argument, and the PRE argument.